In exploration spaceflight, our crew members are going to be asked to do partial gravity EVAs, and in order to do that, the exercise hardware needs to sit in a vibration isolation system, and it is important that it interacts well with the exercise hardware and allows the crew members to perform high-intensity aerobic exercise and high-load lifts such as squats, deadlifts, and bench press.
Other challenges with the exercise system, which includes the VIS, would be ensuring that we can have minimum power, up mass, and operate within a limited operational volume of these small confined vehicles.
The purpose of designing an active VIS is so that we can look at the ways that you can increase the range of exercise that can be done on the same exercise device without worrying about the loads going into the spacecraft structure.
What we're doing here on the ActiVis project is building one vibration isolation device that's going to work for potentially several exercise devices and many exercise modalities within those devices. The VIS problem is really difficult to solve in 1G. To get around that, we did most of our work in analysis and model-based design, and then we used that analysis to feed our mechanical design and determine what type of kinematic chain we would need.
We put our test subjects in a gravity offload system called Argos, and that lets them exercise as if they were in 0G. And then we take motion capture data from that and we introduce it into our digital astronaut simulation. We use these simulations to calculate power requirements, to calculate mass requirements, to look at deflections in the system and how stable the system is.
We place passive retroreflective markers on the test subject at strategic locations. By tracking these markers, we can then use them to drive our biomechanics models. Then in our biomechanics software, switch it to microgravity to get the microgravity forcing terms. Then provide outputs which can feed into our VIS simulations.
We have a linear magnetic encoder that measures the position of the mass, and that allows us to understand the workspace limitation as well as stabilization information. The ActiVis system is a single degree of freedom testbed that will be scaled to a full 6 degrees of freedom.
The simulation is integrated with a single degree of freedom prototype so that it drives the hardware as if it were one leg of the larger VIS system.
We used a commercial actuator in this early study, and we found that its overall profile is much larger than it needs to be to accomplish what we would like it to accomplish. We will most likely need to design our own actuator.
For this single degree of freedom testbed, we're using the EtherCAT technology because it can do high throughput communication, and importantly, it's very deterministic. High reliability, high determinism are very important to the proper functionality of the system.
Right now, the most robust countermeasure we have to guarantee performance of these tests is exercise hardware. It's critical that we design these well now, and we continue to design these well for our future exploration vehicles in order to ensure that we meet NASA's goals of future exploration performance activities.